Hey guys, welcome to the second half of Chemical Kinetics, the second module in Chapter 14. Today we are going to continue on in Chapter 14. We're still going to talk about concentration at time A, concentration at time B, but instead of relating it to rate, which is a little bit arbitrary, we're going to relate it to time. So here we see some CFCs. So CFCs are a well-known pollutant in our atmosphere. And then when we're looking at these CFCs and how long they last in the atmosphere, we could talk about it as, okay, I've put 0.5 molar concentration into the atmosphere. It breaks down at a rate of ABC. But that doesn't really tell us a whole lot. What would be more useful information is if we know what concentration of CFC we put into the atmosphere. We may want to know, like, well, how much is left over after 20 years and 50 years, and how much is left over after 100 years, right? So that's something that might give us a clearer picture of how these are affecting the atmosphere, and then how long they're going to affect the atmosphere as well. So what we're going to do today is we're going to apply calculus to the rate law that we've been talking about. So we're going to apply calculus to a rate law. It's going to give us a new equation, and this equation is going to give us a relationship between the concentration of a reactant and then the time that it's going to be around, how long it's going to last. So here are the two equations that we talked about in the first module of chapter 14. So we talked about this instantaneous rate over here, this average rate of the reaction. And then we talked about this rate law over here. So rate equals the concentration of our reactant times this constant K. So we're actually going to combine these two formulas, so they both equal rate, right? They equal the same thing. We're going to combine these two formulas to look something like this. And then we are going to integrate them. So integration is just a calculus function, right? It's something that we can do in calculus. Calculus is not a prereq for this class, so of course I'm not going to require you to do the integration. What I'm just telling you, for those of you that do have a calculus background, how I get from this formula to the next one is I integrate and then I rearrange the formula. So integrate this formula, and here is our new integrated rate law. And this is for a first order reaction. Okay. So let's break down this equation a little bit. And then we're going to talk about how useful this is to us. So this right here is the natural log. This natural log piece came into the picture through the integration. So when you integrate a certain type of variable, natural log just spits out. It's the fun in calculus here. So that's where this natural log came from. It just came from the calculus that we did. This right here in brackets is going to be the concentration of our reactant A at some time t. So t is going to be later on. That's going to be our final time. So after 10 seconds goes by or 50 years goes by, what's the concentration? So that's this. That's going to equal negative K. So that K is the same K that we saw in the, that K is the same K that we saw in the rate law. So this K is the same thing that we've been dealing with. T is going to be our time, whether it's in seconds or years, whatever it may be in. So T is just time plus the natural log of the concentration of our reactant at time 0. So we're going to know the initial concentration of our reactant. We're going to let some time go by, and then that would be the final concentration of our reactant. Okay. So those are the variables that are in this equation. Concentration is going to be, again, molarity. So the number in these brackets is going to be a molarity. Time is typically going to be in seconds, or you may see it in years. So you just have to kind of take a look at the problem to see what the time would be. And then the units for K, again, are going to depend on what the order of the reaction is. So this is a first order reaction, so the units of K are going to reflect a first order reaction. Okay. So this formula, I integrated it, I rearranged it. Well, why did I rearrange it in this particular fashion or manner? So way back in your algebra days, remember we had the equation for a straight line. So the equation for a line is something like this. Y equals mx plus b. Okay. So let's talk about these different pieces of a line. So y is going to be the y-intercept, or it's going to be where this line intersects the y-axis, okay? So y-intercept is going to be where this line intersects that axis. Okay. X here is going to be the x-intercept. Okay. The x-intercept is going to be where it crosses the x-axis, right? Okay. What else do we have here? Well, this m is the slope. Okay, so if m is positive, it's going to be a positive slope. If m is negative, it's going to be a negative slope. Okay. So looking at this equation of our line and relating it to this y equals mx plus b, what we see is we've got actually this formula right in front of our eyes. Okay. So this natural log of the concentration of A at time t is going to be y. K is going to be the slope. So K is going to be the slope of our reaction. T is the x. And then this B right here is the natural log of A at time 0. Okay. So what we'd see is that we've got an integrated rate law, and then we rearrange the integrated rate law to match up this equation of a line. Okay. So here's the application of it. Right? So for a first order reaction, we can plot the data. So right here, we've got the natural log of the concentration of our reactant. Down here, we've got time, which is important, right? We want time and not rate. And then when we graph this line, it's going to have a negative slope, right? Because of this negative sign right here. And the slope of the line will equal K. So if I can throw this information into my calculator or into Excel, and I get the slope of this line, I can very easily solve for K that way. Okay. So just a slightly different way to determine the rate of our reaction, but still we've got to get this information from experimental data, right? We can't just make it up in our heads. So let's look at an example. Let's throw some actual numbers on here. So let's say we collected this data. Temperature remained the same. We somehow monitored the concentration of this reaction. And so every 100 seconds, we measure the concentration of our reaction. So we saw that the concentration continues to go down as the seconds tick by. So that's nothing surprising. Okay. Then I take this data and I throw it into a graph. So instead of looking at the concentration, I would look at the natural log of the concentration, and I would throw that number into my Excel data sheet, and I would plot time versus the natural log of the concentration. And what you're going to see is if this is, in fact, a first order reaction, this first order reaction, the data is going to fit along this line very nicely. So if I plot natural log of our reactant versus time, I get a nice straight line. When you're in Excel or even on your calculator, you can ask for the equation for that line. So you can say, hey, Excel, I want the equation for this line that I just plotted. So Excel is going to spit out something like this, right? So y equals mx plus b. So if you can identify this guy right here as your slope, so your m, so m equals slope, and then the application for us is that's going to be our k value. So the k value for this particular equation is negative 0.000290. So this could be another way that we could determine the order of a reaction. So if we can monitor concentration, if we can monitor time, throw that into a graph. This is one way we could determine is that first order, second order, third order. So let's look at an example of this. So how would we apply this to a test? How would we apply this to a problem? So let's look at this example. Okay. In the previous example, we determined SO2Cl2 is a first order reaction, and it has a rate constant of 2.9 times 10 to the negative fourth. If the reaction is carried out at the same temperature and the initial concentration is 0.0225, what would be the concentration after 865 seconds? So take a minute to just kind of mull through this question, maybe start to gather some of your data, pause the slide, gather some of your data, pause the video, and see how far you can get into it. Then I'll catch up to you. All right, so I'm going to flip ahead so I have some room to work. So here's my equation. Just to start, I always like to take inventory of what I know and what I'm trying to solve for. So the different pieces of the equation that I might need are the concentration of A at some time. I'm going to need the value for K. I'm going to need the time and the concentration of A at initial time or time 0. Okay. So let's go back and read through this again. So we determined it's a first order reaction, which means we can use this equation. The rate constant is 2.9 times 10 to the negative 4. So that's K. And with this being a first order reaction, there are my units for K. So 1 over S, or S to the negative 1. Okay. If the reaction is carried out at the same temperature, so what we'll see actually this week in lab is that these are temperature dependent. So same temperature is just telling us we can continue to use this equation. The initial concentration is 0.0225. So initial concentration means at time 0, before I put anything into the beaker, before I started this reaction, the initial concentration was 225, and that's a molarity. Okay. What is the concentration after 865 seconds? So time in this case is 865 seconds. And we're trying to determine, well, what is the concentration after those seconds go by? Okay. So we have all but one of the variables. So now we just need to plug and chug, plug it into our equation, and chug through as much as we can. So the natural log of A at time t, so that's what we're solving for. equals negative K. So K is 2.90 times 10 to the negative fourth, 1 over seconds. And we're going to multiply that by time, which is 865 seconds. And then we're going to add that to the natural log of the original concentration. So 0.0225 molar. Oh, that's in parentheses right there. Okay. All right, so let's clean this up a little bit. Let's plug some of these values into our calculator and just clean up the right-hand side. So over here we still have natural log of A at time t, so we're still trying to solve for that. First, I'm just going to multiply these two numbers together. So I've got negative 2.9 times 10 to the negative fourth times 865. And I get negative 0.2. Negative 0.25. And we see that this becomes unitless. So seconds on top, seconds on the bottom, those cancel. So it becomes unitless, if you will. And then for this part of the equation, let your calculator do the heavy lifting here. So you're literally going to find the natural log button on your calculator. So I'm going to hit ln, natural log, and then I'm going to type in the number 0.0225, close my parentheses, and hit equals. So that tells me that the natural log of that number is negative 3.79. Okay. All right. So again, I can do one more step to clean up the right-hand side of the equation. Be very, very careful with your negative signs here, so make sure you don't miss them. They get missed pretty easily. So natural log of A at time t is going to be negative 0.25 plus negative 3.79, and that's going to equal negative 4.04. Well, how in the world do we solve for the concentration of A when it's got a crazy natural log in front of it? Okay. So how in the world do we essentially cancel out or get rid of that natural log? So again, we're going to take it way back to your algebra days. To get rid of natural log, we're going to use Euler's number. So that E, that crazy E that's on your calculator. So I'm going to take the E of both sides. So I'm going to take E and raise it to the power of natural log of A. And whatever I do to the left side, I also have to do to the right side. So I'm going to take E raised to the power of negative 4.04. Okay. So what Euler's number does is it essentially is the reciprocal or the opposite of this natural log. So it essentially cancels out the natural log. So this side, the left-hand side of the equation, just becomes the concentration of A at time t. So that's what we're trying to solve for anyway. And then to solve for the right-hand side here, again, we're going to let our calculator do the heavy lifting. So I'm going to find that E button on my calculator, and on my TI-84, it's in blue right above the natural log button. So I'm going to hit the E button, and it raises it to the power. It already has that in there. And then I'm going to type in negative 4.04, close my parentheses, and it spits out a number like this, 0.017, if I round up, 6. And that's a concentration, so I'm going to put molarity on the end. Okay. So a couple old school algebra tricks here to get us to the answer. Remember, if I teach you nothing else this semester, I want you to take the time to step back and say, does this make sense? So if I started with 0.0225 molarity, I let this reaction go for 865 seconds. Does it make sense that the new molarity would be 0.0176? And that should make sense. The molarity goes down. That's what we would expect to happen. So that number does make sense to us. So that is the answer for this particular problem. Okay. All right. So here's another example. What I want you guys to do is go ahead and pause the video, take a moment to try to work this out on your own, and then I'll hit play and I'll work through it with you. All right, so the reaction is a first order reaction. So that just tells us that we're going to use the formula that we've been talking about. It has a measured rate constant of 3.36 times 10 to the negative 5. If the initial concentration is 0.0445, what is the concentration after 235 seconds? So let's click forward here and start taking inventory of what we know and what we need to solve for. So this problem looks very, very similar to the one that we just did. All right. So first order reaction, so we're going to use the natural log equation. It has a rate constant of 3.36 times 10 to the negative fifth. So that's our K. It's still first order, so 1 over seconds is the unit for that. Oops, other way. Initial concentration is 0.0445, so that is the concentration of A at time 0. Plus. Right. And then it what is the concentration? So we're going to let 235 seconds go by. So time is 235 seconds. We're solving for concentration at that time. Okay. So let's plug and chug. So the natural log of A at time t is what we're solving for. That's going to equal negative K is 3.36 times 10 to the negative fifth, 1 over seconds, times time, which is 235 seconds. We're going to add that to the natural log of the initial concentration. So let's clean up the right-hand side step by step. So 3.36 times 10 to the negative fifth times 235 seconds. We get negative 0.00789 plus, and then I'm going to type in natural log of 0.0445, and this is negative 3.11. Okay, so clean up the right-hand side one more time. So negative 0.00789 plus negative 311, and I get negative 3.12. Okay. So again, to get rid of natural log, we're going to use Euler's number. So E raised to the natural log of A equals E raised to negative 3.12. So the concentration of A at time t, so Euler's to the negative 3.12. And the concentration is 0.0442 molar. Does that make sense? Well, we would expect it to go down. And it does, in fact, go down. So, yes, that makes sense. So, I'm going to wrap up the video there. So, that's the integrated rate law for a first order reaction. I hope you guys found this helpful.